Well, for our last example in this section, we're going to discuss an important theorem and then summarize what we've talked about. The important theorem is something that you'll see even more in calculus. It's called the intermediate value theorem. Let's see if we can figure out what goes in the blank here. If a polynomial function, if f is a polynomial function, and f of a and b, f of a and f of b have opposite signs, so one of them is positive and one of them is negative, then there's a number c that falls between a and b for which blank. Well, let's think about that. Let me just draw a little tiny picture here. And I didn't say whether a, which is bigger, a or b, so it doesn't matter. I'll say b is here, and I'll say a is way over here. And f of b and f of a have opposite signs. So I'm going to make one of them positive above the x-axis, one of them negative below the x-axis. Well, what do you think? A polynomial function, remember, is continuous. If the graph is going to go from this point continuously and smoothly up to this point. You know, from this point to this point. So at some point, no matter what, it's going to have to cross the x-axis. So that would be the point C we're looking for. And how do I state that? There's a number c in between a and b such that, what is f of c here? 0. F of c equals 0. That's the intermediate value theorem. Now, this may look difficult, but it's not. It's very simple. We don't have to graph this polynomial function. All we have to do is show that f of x equals 3x cubed minus 10x plus 9 has a real 0 or a real root somewhere between -3 and 2. And if without this theorem, you might think, oh my goodness, I need to actually find that 0. But we don't have to at all. Let's compute f of 3 and let's compute f of 2. If they have opposite signs, we're done by the intermediate value theorem. So let's see. What is f of -3? It's 3 times -3 cubed minus 10 times -3 plus 9. All right, what is that going to be? -3 cubed, 3 times 3 times 3 is 27. So that'd be -27 times 3, which is -81. But then this is plus 30 plus 9. And it's obvious that this is negative, right? -81 and then plus 39. But let's see what that would be. It would be -41, not -41, but -42, I think. The important part, even if we got that wrong, is we know that's negative. Yeah, I think that's right, -42. And then f of 2 is equal to 3 times 2 cubed minus 10 times 2 plus 9, which is 2 cubed is 8, 8 times 3 is 24, minus 20 plus 9, that's positive. Let's see if I get this right. 4 plus 9 is 13. Positive. That's all we had to do. That means that somewhere between -3 and 2 on the x-axis, it's going to cross the x-axis. So there is a real 0 between -3 and 2 based upon what we did here. We don't know what the value is. We don't know where that is, but somewhere between -3 and 2. Okay, let's summarize what we've done in this section. All right, for graphing a polynomial function of degree n, how do we determine the graph's end behavior? What's one way of doing that? We can simply look at that leading term and use the leading coefficient test that we saw in an earlier video. That'll tell us whether it rises or falls left. and whether it rises or falls right. Okay, then we set the polynomial equal to 0. We have to factor the polynomial to do this. To obtain the, since we're talking about graphing, I could say roots or zeros, or I could find the solutions, but I'm going to say x-intercepts. Some of the most important points that you should graph. And what does this mean? Determine T or C. Determine whether it touches at each one of these x-intercepts or whether it crosses. It touches without crossing if the multiplicity of the x-intercept or the multiplicity of the root or 0 is an even number. If the multiplicity is odd, it crosses right through the x-axis. And then we compute the y-intercept. That's a nice, easy point usually to get. It's f of 0. Just plug in 0 to f and you'll get the y-intercept. This is an optional one. It can help you if you happen to notice that the function is an even function. That means that there would be symmetry around the y-axis. And one thing you could do for an even function then is just plug in values of x that are positive. And then when you're done, since it's symmetric, a mirror image around the y-axis, you could just copy whatever you've done on the right, do the mirror image on the left. So you'd really only have to plug in half the number of points if you wanted to. And then symmetry about the origin means it's an odd function. You can go back and review that. And then remember that there are at most, in what I call ups and downs, or at most n minus 1 turning points. And remember that n is the degree of the polynomial. So if it's a degree 5 polynomial, you're going to have at most 1, 2, 3, 4, 5 ups and downs. Okay, let's graph. Let's do one final example in this section. Let's graph x cubed minus 3x squared, which, if we factored it, is equal to, pull out an x squared from both terms, and x squared times x minus 3. Well, that was easy to factor. So the zeros are set this equal to 0, and we get a 0. Set this in parentheses equal to 0, and we get x equals positive 3. So let's see, it's going to be real informal here. I'm drawing my own xy plane. So we've got a 0 at 0, and then 1, 2, 3. All right, well, what do we know about the, this may not be a big deal, but I'm going to go ahead and write down what the multiplicity of each 0 is. 0 has a multiplicity what? Remember, we set this equal to 0 to get 0, and its multiplicity 2. And we set this equal to 0 to get 3 as a root, and its multiplicity is 1. So it's going to cross through it at 3, and it's going to touch without crossing at 0 because 2 is even and 1 is odd. If we just look at the end behavior, I think that's pretty much all we need to do to make this graph. On an exam, I'm not expecting you to plot 10 or 12, some big number of xy pairs. I want you to get every intercept correct, and by the way, note that we have the y-intercept here as well. But I don't expect you to plot 3 points here and 3 points in the middle and 3 points to the right. I want to see the ups and downs correct. I want to see all of the intercepts correct. I know you'll have limited time on an exam. Okay, so let's do the end behavior. Learn how this can help us so that we don't have to plot so many points. The end behavior, we look at the leading term and use the leading coefficient test. the leading coefficient is positive and the degree is odd. That means it's going to fall left, rise right. Okay, so that means it's going to, the rise right part means that it looks like that. The falls left part means it's going to look like that. So there's really only one option. Since we know that it touches without crossing, maybe I'll put touch cross. It touches at 0 without crossing, it's going to do that. And then it crosses through at 3, so there's no other way but just to connect it like that. And really, this is about the level of detail on an exam that I want you to go through for graphing a polynomial like this. Get all of the intercepts correct, and then make sure the ups and downs are correct. The end behavior is correct. Another way of doing it, if you forgot about the end behavior, would just be compute some test points. 1 or 2 to the left of this one, 1 or 2 in the middle, 1 or 2 to the right. You'd find out that if you come out here, you get a negative number. If you go in between them, you get a negative number. And if you go to the right of this one, you get a positive number. And that would be enough information to give you this graph as well.